Hello, my name's Mark Wally and welcome to this video, the first in a series of 3 videos looking at calculations in electricity. In this video, we're going to cover the background theory. We're going to look at the various equations that we're going to use and how they're related. In video 2, we're going to look at a way in which we can answer very challenging questions. And in the third video in this series, we're going to look at a set of worked examples for electricity calculations. In this video, we're going to focus on 4 of the 6 equations that students have to learn. We're going to cover those that deal with potential difference, current, resistance, energy, and power. These all link together nicely and can also be related to the rope model. And so during this session, we'll see how they can be used and how they can be tied together. At this point, it should be noted that the energy transferred by the current is equivalent to the electrical work done by that current. Ultimately, these equations are our tools in predicting the behaviour of a variety of destination stores and calculating the value of key measurable quantities. Before we start to look at the equations, we're going to take a couple of diversions into 2 important topics, which we will cover very briefly. The first of which is the apparent contradictions that we see in the use of quantities and their symbols as experienced in equations. Some are obvious, using the symbol R to represent resistance, even though its unit is the ohm and has a unit symbol of the Greek letter omega. However, elsewhere it can be a little bit more confusing. For instance, charge is represented by the symbol Q, and potential difference by the symbol V. These are things that students simply need to learn. And as a consequence, it might be the source of a good activity for retrieval practice. We also need to look at units. This is important when doing physics because we should always be working in the simplest SI units, for instance, joules, watts, seconds, amps, and volts. However, we often find in physics questions that more complex forms of these units are found, such as kilowatts, kilojoules, minutes, and sometimes as well milliamps and millivolts. Now, what's important is that we can convert these back to watts, joules, seconds, amps, and volts. And it matters that students can actually do this conversion for themselves. And so to convert kilowatts to watts and kilojoules to joules, we need to multiply by 1,000. To convert minutes to seconds, we need to multiply by 60. And to convert both milliamps to amps and millivolts to volts, we just divide by 1,000. Let's look at how these equations are connected and why they are so important. So the equations don't stand alone. If we look at them in turn, we'll see that there are relationships between all of the quantities. So let's start with V equals IR, the equation for potential difference equaling the current multiplied by the resistance. Now related to that is the equation for power. Power is current times potential difference, and we can see how much they've got in common. Remember what power is. Power is the rate at which energy is transferred. So that actually gives us the next relationship, E equals PT. The total energy transferred is the power, the energy transferred every second, multiplied by the time for which that process is taking place. Now, of course, here's the key bit, that because we can come up with a number for the energy by evaluating power times time, then we can utilize the conservation of energy. And that can lead us into all of these stores. It can lead us into the kinetic energy store, the potential energy store, the thermal store, and so on, and allow us to do calculations when energy is transferred from one system to another. Hence, all of these equations tying together. And later on, we'll look at a particular worked example actually using this. So let's start off by looking at one of the most famous equations in all of physics. V equals IR, potential difference is current times resistance. It's a peculiar equation because actually, though it appears often as V equals IR, does it really represent the physics that we're often teaching? Let me put this to you. When we construct a circuit, what we tend to do is that we tend to be in charge of the potential difference. We're the ones who place the batteries in the circuit or the power supply. And then in addition, we're in control of the resistance by the component that we actually insert into the system. The potential difference and the resistance are the independent variables, and the outcome of this is the current. So in fact, I tend to find that I equals V divided by R is a more useful form of the equation as it tells us a physics story. And this relates nicely to the rope model. And if you're using the rope model with a class, you may wish to derive this form of the equation, because after all, if you increase the potential difference, the V, you're pulling harder. And what happens as you pull harder? Well, the rope moves more quickly. The current increases. So we see the relationship immediately between potential difference and the resultant current. On the other hand, if you increase the grip on the rope, if you increase the resistance, what happens? The rope slows down. And so the current decreases. And there we see the inverse relationship, which is inherent within I equals V over R. The other form that we do often use is R equals V over I. And when do we use that? Well, we use that for finding an unknown resistance. So now let's move on to the next set of equations. There are a pair of equations which cover power, P equals IV and P equals I squared R. Let's start off by considering what power is. Power is the rate at which energy is transferred from one store to another. And what's really useful here is to think about the units of power. Power is measured in watts, in joules per second. And that per is a key word, it means every. So it's the number of joules of energy transferred every single second. So P equals current times potential difference, P equals IV. And from this, and using the equation we met in the previous slide, V equals IR, what we're able to do is perform a little bit of algebra, which we'll look at in a few moments' time, and derive that power is also I squared R. Now, this is a very important equation, and it's a very useful equation. What it actually tells us is that for certain appliances, let's say a kettle, what's most important is actually having a large current rather than having a large resistance. The current goes up as the squared of the current, whereas the resistance is just linear. So the effect of increasing the current is far greater than the effect of increasing the resistance. Now, let's go back to P equals I squared R. You may wish to derive this with your students. To derive it formally, this is how we do it. We start off with P equals IV. And then we look back to V equals IR, and we'll call V equals IR equation 2. Now you'll notice that in equation 1, there's already a V, a potential difference. So we can take equation 2 and substitute that where V appears in equation 1. So that we then get P equals I, which is present in equation 1, multiplied by, and rather than V, we're going to substitute in IR. So we get P equals I times IR, and I times I is I squared, and so we get P equals I squared R. Now, of course, some students find the act of substitution quite tricky. So here's a way of doing it using some cards as a resource. So here's a simple little resource to help with performing substitutions. And it's something that you may find useful elsewhere in physics. We've got in front of us P equals, and then nothing. So what we're going to add are these cards. What I've done is on one side I've put I, and then on the other side is what it equals. So that's from rearranging V equals IR. So you'll remember from a couple of slides ago that I equals V over R. So that's going to be that one. Similarly, here we've got V. Now we know that V equals IR. So there is our equation. So we're going to do some physical substitution. P equals IV, but V equals, and I turn it over, IR, which is I times I, which is I squared R. And that's a quick and simple way to show students how to do a substitution. So now let's move on to the final equations, the equations for energy. We've already met the concept of power and what it means. And so now what we need to do is extend that to energy. We know that power means the number of joules of energy transferred every second. So the total amount of energy transferred will just be the power multiplied by the time. In other words, for instance, if you are transferring 5 joules of energy every second, 5 watts for 10 seconds, you'll see that after 10 seconds, you've managed to transfer 50 joules of energy. And so there's the equation, energy is power times time. Now notice, we've got a P term there, and we've already met the idea that P equals IV. So we're able to produce a final equation by substituting IV for P, which is circled in that equation. And we're able to come up with an equation for the energy transferred due to the electrical work done, which is E equals IVT, the current times the potential difference times the time taken. So why is that so important? Well, here's the thing. It allows us to work out how another system will behave when electrical work is done, resulting in energy transfer to a destination system. And so we can predict the behavior of that destination system, whether that's a mechanical system, whether it's a thermal system, whatever. But we're allowed to do a calculation which will give us a prediction which will be measurable. So here we see it in a graphic, that E equals PT and that equals IVT. And this gives us a measure of the electrical work done, and assuming that no energy is transferred to the environment, if it's all transferred to the destination system, we can then predict the outcome and the behavior of that destination system. And this is the whole point of the concept of the conservation of energy. Finally, it's worth going back as well to the rope model, because intuitively the rope model tells us that E equals IVT. What do students experience as that rope is pulled through their hands? They experience warming up. And so it's no surprise that the harder we pull, the faster the rope goes, and the longer we do it, the more our students' hands warm up. In other words, the greater the amount of energy transferred in the rope model. So to round off this video, we're going to look at an example. We're not going to solve it in this session. We're going to save that until video 2. But the purpose of having a look at it is so that we can understand that by performing calculations for energy or work done in an initial system, in this case a circuit, it allows us to predict the behavior of the destination system and allows us to calculate changes in some measurable property. And in this case, it will be temperature. So this will be quite a familiar type of example. An immersion heater is connected to a supply with a potential difference of 12 volts. As a result, a current of 4 amps flows through the heater. The heater is placed in a 1 kilogram block for 5 minutes. Assuming no transfer of energy to the environment, calculate the temperature change in the aluminium block. The specific heat capacity of aluminium is 900 joules per kilogram per degree C. And of course, this will be familiar as one of the required practicals. First and foremost, it's useful just to unpack the question and consider what we're feeding into the question and what we're looking to calculate. So in this case, the initial system data in the electrical circuit is the potential difference of 12 volts, a current of 4 amps, And in addition, this is being fed into an immersion heater, which is placed in an aluminium block with a mass of 1 kilogram. And it's in there for 5 minutes, 300 seconds. The electrical work done by the current results in a transfer of energy to the thermal store of the block, causing a temperature change, which is determined by a material property, the specific heat capacity of the block, which is 900 joules per kilogram per degree Celsius. And as a consequence, we're going to get a temperature change, which is the whole point of the question, to calculate what will happen and to give us a measurable, because ultimately that's what physics is about. It's about working out measurables so that we can test predictions against reality. So what's happening in terms of work and energy then? So in the initial system, the input system, what we want to do is calculate the electrical work done, the energy being transferred by the current. And assuming that no energy is being transferred to the environment, that it's only being transferred to the aluminium block. Conservation of energy allows us to assume then that all of that energy is transferred to the aluminium block, and we're able to calculate the temperature change using one of the other equations, in this case E equals mc delta theta. So in the next video, we'll actually look at a way of solving this problem. But for now, that brings us to the end of the first in this set of 3 videos. I hope you found it useful, and I do hope you'll join me for the next video when we look at solving more complex questions. Hello, my name is Mark Wally and welcome to this video. This is the second in a series of 3 videos looking at calculations in electricity. In today's video, we're going to be looking at how we can answer challenging questions using a generic framework, which can also be applied to lots of other situations within physics. In the previous video, we looked briefly at this question without solving it. In this video, we're going to look at a way to solve this question. In this question, we have an immersion heater, and that is supplied with a potential difference of 12 volts, which results in a current of 4 amps flowing through it for a period of 5 minutes. We're going to assume that no energy is transferred to the environment, and as a consequence, we're going to calculate the temperature change in that aluminium block. Now, this is a more challenging question, because when we consider the equation that we're going to use to calculate temperature change, we'll notice that we're not apparently given all of the information. So how do we go about answering questions like this one? I'm going to present to you now a method which can be used in lots of different situations. You'll notice on the screen I've also copied the key information from the question, and we'll use that presently to actually go through the process of evaluating an answer. So when answering a question like this, the first stage should be deciding what you're being asked to find out. After you've decided what you're being asked to find out, identify the equation most likely to give you the answer. When you know that, go back to the question and identify the data that you've been given and how this matches to the equation. So find out what information do we have, but what information don't we have? Then, when you've discovered what it is you've not been given in the question, find an equation for that missing quantity, which also utilizes the other quantities given in the question, but not used earlier on. Take that equation, if you need to, rearrange it and perform the calculation. And finally, use the value that you've just obtained in the previous stage back in the original equation to evaluate the final answer. Now let's look at solving the problem that we've seen earlier using the 6-step framework. So the first stage in that framework is being asked simply, what are you being asked to find out? So if we look at the question, we are asked to calculate the temperature change in the aluminium block. So what are we being asked to find out? Being asked to find out temperature change. And let's give it the correct symbol, delta theta. And so what is the equation? Well, we can see that the question includes the specific heat capacity. We can see it includes a mass. We've got a temperature change. So the equation that we'd be looking for is E equals mc delta theta. Now we are asked for the temperature change. So at this point, what it's worth doing is changing the subject. And in this case, it would be delta theta equals E divided by mc. The third stage is about identifying quantities, which the question gives us or in fact doesn't. So let's have a look at what the question already provides. Well, we're looking for E, M and C. Well, we can see here 1 kilogram. That's what we do have. So we've got 1 kilogram. We can also see that we're given C, the specific heat capacity, which is 900 joules per kilogram degrees C. But what we're not given is E. That is a quantity we're going to have to evaluate. So stage 4 asks us to find an equation for the missing quantity that involves the other information in the question. Well, if we look at the rest of the question, we can actually see that we've been given a potential difference of 12 volts. We can see we've been given a current of 4 amps. And we can also see we've been given a time of 5 minutes. So is there an equation which links those quantities to the missing quantity in our first equation? And yes, there is. It's E equals IV T. The reason being in this case that IV is actually the power. So the fifth step in all of this is to rearrange if necessary and calculate. Well, in this case, we don't need to rearrange because E is already the subject of the equation. So E equals I, which is 4 amps, times the potential difference, which is 12 volts, times the time. Now note, we've got 5 minutes and we have to work in SI units. So 5 minutes is of course 300 seconds. And if we calculate that, we get an answer of 14,400 joules. The very final stage of this process is then to take this value and to substitute it back in here, along with the values for the mass and the specific heat capacity. And so finally, we can write that delta theta is the energy which we calculated in step 5, divided by the mass, which in this case is 1, times the specific heat capacity, which is 900. And if we evaluate that, we get an answer of 16 degrees Celsius. So this is a method that can be employed not only on this type of calculation for linking electricity and thermal energy, it can be used elsewhere, often on 6-mark questions where there is apparently a missing equation. Well, hopefully you found that approach to answering challenging questions useful, and maybe you can find applications of that elsewhere in physics. In the next video, we're going to work through a set of typical questions that may be met at GCSE. I hope you can join me then. Hello, my name is Mark Wally and welcome to this video, the third in a series of 3 videos looking at calculations for electricity at GCSE. In this, the third video, we're going to work through 5 problems which students may encounter at GCSE. These 5 problems, which I'll present under the visualizer, cover a range of questions from simple series circuits to more complex 6-mark questions. This first question is very familiar, and it features a 40 ohm resistor with a 12 volt power supply across it. And we're being asked in the question to calculate the current flowing through that resistor. To answer these questions, we're going to use a standard calculation framework to help us order our working. So let's start off with answering this question. What quantity do we want to calculate? Well, the question asks us to calculate the current, and that has symbol I. What quantities are given in the question and what are their values? Well, we can see we've been given a resistance, R equals 40 ohms. And we can also see that we've been given a potential difference, the symbol for which is V, and that equals 12 volts. And what formula links I, R, and V? And it's going to be V equals I, R. Now, what form should that formula take? Well, we're being asked to find I, but we can see that I isn't the subject of the equation. So what we need to do is change the subject, and that will look like I equals V over R. And the final stage is to substitute in the values. So I equals 12 divided by 40, and that will give us 0.3. Don't forget the units, it's a current, so it's measured in amps. Question 2 is similar to question 1 in that we have a single component in a circuit. However, this time, as you can see, we're being asked to calculate the resistance of the object. In this circuit, it's a filament bulb. So again, let's use a standard calculation framework to solve the problem. This time, we've been asked to calculate the resistance, symbol R. And what quantities are given in the question? Well, we have a potential difference of 12 volts, and we have a current of 0.4 amps. As with the previous question, the formula which links all of these quantities is V equals IR. Now we're being asked to find the resistance, and it happens that in this formula, resistance is not the subject of the equation. So the first thing we need to do is then make R the subject of the equation, which is R equals V divided by I. And the final stage is to substitute and calculate. So R will equal the potential difference, which is 12, divided by the current, which is 0.4, and that gives us an answer of 30 ohms. And again, don't forget the units. Question 3 is a more challenging question. And what we can see now is that we have two resistors in series, a 16 ohm resistor and an 8 ohm resistor. We have a potential difference of 6 volts across both of these resistors. And we're being asked to calculate the potential difference across each of these resistors. Now, the first thing to note is that the current at any point in this circuit will be the same. And so that's going to give us a handle on the problem. So to solve this question, what we need to do to start with is think about the current in the circuit. So we want to calculate the current in the circuit. Now, to do that, we actually need to find the total resistance. Now, in a series circuit, the total resistance is actually just the sum of the two resistors in series. We'll call them R1 and R2, and that will be 16 plus 8, which is 24 ohms. Now, we can imagine those, in this case, to be a single resistor. And if that were the case, we'd have 6 volts across a 24 ohm resistor. So let's use V equals IR. We have the potential difference, which is 6 volts. And we have the resistance, which is 24 ohms. And the thing that we're looking for is the current I. So let's make I the subject of that equation. And we get that I equals V over R. And substituting in values, we get 6 divided by 24, which is a current of 0.25 amps. Now, importantly, that's the current at any point in this circuit. And for us, it's the current flowing through both the 16 ohm resistor and the 8 ohm resistor. Now, because that current's flowing through them, there must be a potential difference across both of those resistors. And so we're going to use this equation again, actually in its original form. So for the 16 ohm resistor, we're going to say that the potential difference, V, is the current times the value of that resistor, which will be 0.25 times the value of the resistor, 16, which gives us an answer of 4 volts. For the 8 ohm resistor, we do the same thing again. The current multiplied by the resistance, which is 0.25 times 8, which is 2 volts. And you'll notice as well that if you take the 2 volts and the 4 volts and add them together, you get back to the 6 volts, which is the potential difference across both of those resistors in series. Question 4 is a slightly more complicated question. Rather than being asked to calculate either potential difference, current or resistance, this time we're being asked to calculate the rate at which energy is transferred and also a total amount of energy transferred in a certain amount of time. So to answer this, we're still going to use the framework that we've used earlier, but we do need to give a little bit of extra attention to what we're being asked to find out. The rate at which energy is transferred, how much energy is transferred in a certain amount of time, is actually the power. And so, what quantity do we want to calculate? We actually want to calculate the power, symbol P. What quantities have we been given in the question that will help us with this? We've been given a potential difference, V equals 12 volts. And we've also been given a current, I equals 0.6 amps. And so what we're now looking for is the formula that links P, I, and V. And that's the familiar formula. Power is current times potential difference. Now, previously, we've been required to change the subject of that formula. However, we can see we're being asked for power, and it's already in the P equals IV format. And so we simply need to restate that we want P equals IV, and now finally we can substitute and calculate. The current is 0.6 multiplied by a potential difference of 12, which gives us a power of 7.2 watts. And remember that 1 watt is 1 joule every second. We're going to need that value in a moment as we tackle part B. So part B asks us to calculate the amount of energy, the total amount of energy transferred in 2 minutes. So again, we can use the same framework. What quantity do we want to calculate? Well, this time we're actually after energy. And energy has the symbol E. What quantities are given in the question? Well, we're given a time, T equals 2 minutes. But remember, we must work in SI units. A minute isn't an SI unit, but seconds are. And so let's convert that to 120 seconds. And what we're also going to do is we're going to take the value we arrived at in the previous part, which was power equals 7.2 watts. Now, the formula which links energy, power, and time is energy equals power times time. And as with the previous part, there's no need to change the subject, and so it just remains as energy is power times time. And so to finish off the question, we need to substitute, and we need to calculate. We had a power of 7.2 watts from the previous part, and we've got a time of 120 seconds. Multiplying those two numbers together gives us a value of 864. And don't forget the correct units for energy, which are joules. Question 5 looks innocuous. However, if we look at what we're being asked to calculate, the energy, we don't immediately know a formula which links resistance and current directly to energy. So consequently, we're going to have to use a slightly more sophisticated approach to solve this problem. This would be typically one of those sorts of questions that would be worth 5 or 6 marks on an exam. So using a different framework to answer the question, one that accommodates what I would call a missing equation, we're going to work through 6 stages. The first stage of which is we're being asked, what is it we need to find out? Well, we're being asked to calculate energy. Symbol E. So what equation is likely? Well, just looking at the question, and there are many energy equations, we need to find the most appropriate one. So we know it's going to have something to do with electricity, and we've got time in the question. So it seems reasonable that the equation we're going to go for is E equals power times time. E equals PT. The third stage is to now look at the question and see the information that we've been given and that isn't present, or at least not directly present. So energy is the quantity we've been asked to calculate. We've been given a time, so that's okay. We've been given 3 minutes. But as I've said earlier, don't forget we can't work in minutes, and we may as well do that conversion here to 180 seconds. We must work in SI units. But nowhere in the question do we see mention of power. That is the quantity which is missing. And so what we now need to do is move on to the 4th step. Find an equation for the missing quantity that involves the other information in the question. Well, let's just firstly look at what the other information in the question is. We can see in the question that we've got a 50 ohm resistor. So we've got an R which equals 50 ohms. And we've also got a current, I equals 0.6 amps. So now what we're looking for is an equation which links power, current, and resistance. And there is an equation that does that. And it's P equals I squared R. Now, to move to stage 5, we need to look if that needs to be rearranged. We can see we don't need to because it's actually power that we're being required to calculate. So now all that we do is substitute in and calculate. So P equals I squared, 0.6 squared, multiplied by the resistance of 50 ohms. And that gives us a power of 18 watts. And now the final stage is to take the 18 watts and to substitute it back in to the initial equation. So we can finally write E equals PT. And let's substitute in the values. We've got the 18 watts, which we've just calculated in stage 5. And we've got the 180 seconds, which is given to us essentially in the question. Multiplying those together gives us an answer of 3,240 joules, remembering to include the units. I hope that you found this useful, along with the other 2 videos in this set of 3 videos on calculations for electricity. Please take the time and have a look at our other videos on electricity, and feel free to use them both for your own development and also in class. Thank you.